Ellen is going to put it on, going to compress and put it in the links together, so you'll get that. I still want to re-emphasize and pass on the message from our sponsor. That is Makerere University Regional Center for Crop Improvement. We offer 2 degree courses at the center, that is Masters in Plant Breeding and Seed Systems, and then PhD in Plant Breeding and Biotechnology. These are high quality courses that any plant breeder would wish to register, or any intending plant breeder would want to do. We also offer short courses. This is one of the courses that is offered through the center. You need to keep checking on us. We'll be offering many additional courses as time progress. So today we're also going to have, maybe we're going to ask the director of the center towards the end to come and make some comments and close the session, and then also Reforum will have their representative say a word or two. We don't take your dedication for granted. We are very grateful for turning up despite that this Saturday, and we are really grateful for that. So I'm going to give you about 10 minutes to download the course material for today. The PowerPoint remained the same with the one in the 10. What we are loading today is we are loading this R script for mixed model, and then we are loading one particular data set that we are going to use to illustrate a mixed model. So 10 minutes, please download, and then we start. I also still request that you get yourself on the Telegram group so that we are able to follow up on several issues, and also you to have link between among us yourself. I think you may need a company which other it was you need bad days for doing research or doing data analysis together. So 10 minutes, please, and then we start off at 10:15. Material, the link has already been shared. We'll keep posting, so please check the chat. The link for the Telegram has also been shared. Please make sure you're on. Not yet posted, the post is going to come. You posted? So the Google link has been sent. Don't worry about the training certificate. We are going to get you training certificate as long as you've registered. We are going to compile all the lists, and then we are going to give the certificate, but you'll give us a little bit of time because we need to compile a comprehensive list so that nobody's left out. That's why I think we need to get some kind of contact. The Google link, the drive is still going to be active for the next 2 weeks. So, don't you can still share that with your friends. So please don't feel like we are going to end everything today. No. And the link for attendance will be sent, please. Just hold on a little bit. There's no sound because we've requested you to take the next 10 minutes, remaining 7 minutes to download the material, and then we start off. We are only downloading two files. The script and then a small data set that we are going to use for illustration. Please help. Dan wants to join the group. Please help with the Telegraph link. Our very most efficient Ellen is going to ensure that everybody get the link. Hey. Just hold on, the links are going to be posted again. Okay, so the registration link and Google link have been sent. Okay. Yeah. So the Google link has everything, and it is always updated very frequently. So please follow the Google link. You get all the material from day one up to today. You can share freely with your colleagues, is allowed. You can use it for your teaching, that's fine. As long as you can acknowledge Susan and Ellen, that's okay. Okay, even me, that's fine. So we are available. You can contact us, but it's a bit of a challenge. Sometimes it takes time is to respond because we get a lot of responses, but we are available for collaborations and other things. Yeah, so if your universities are interested in offering short courses, we can be available. As long as if it is within Uganda, we can walk over there. If it is outside Uganda, then we may need some transport. Yeah, but even through Zoom will be fine if you organize with your professors and they want a short course. If time is available, that is okay. Yes, we are certainly coming to Ethiopia. I think somebody's welcoming us to Ethiopia. And Somalia, good. Ghana, Nigeria. I think only Kenya doesn't want to win. Oh, Kenya is also in, yeah. Cameroon. Oh, now I see everybody. India, Botswana, Kenya, Ethiopia, Nigeria, India, Benin, Zimbabwe, Nigeria, Somalia, South Sudan, Kenya, Benin, okay. Hong Kong. Oh, that is good. Yeah, this is very interesting. Okay. I think we can start now. Oh, 2 more minutes. Then we can start. So please ensure you have the material. I promise to talk about a potential scholarship. We are running intra-Africa academic mobility. In that mobility, we have a few scholarships for short-term mobility. The mobility, the name of mobility is called SCIPSA. I'm going to put it in the chat. So you can, we have a website that you can visit. And from the website, there are some contacts that you can get. You can reach us through the contacts. So the short-term mobility requires that you are registered with your university first. You're a registered student, either master's or MSc. We are mainly interested in fields of plant breeding and crop science. So once you register at your university as MSc or PhD student, you can apply for 6 months to attend courses or do research at Makerere University, University of Eldoret, Cairo University, University of Ghana, and Sheikh Anta Diop University in Senegal. So we can give you up to maybe about 6 months. So the name is SCIPSA. The links are going to, the links for the course are going to be posted, please. Okay, so I'm going to start now. Somebody had requested for analysis of diversity data. I see Ampoza is in the course. You contact Ampoza, can help you. Okay, so let's begin our day. So I'm going to have a brief recap of what we went through yesterday. And then we pick up. Okay, so we started yesterday by looking at application mixed model, and we say mixed model can be applied in one of the areas below. You can use it for estimating the variant components. This one is especially very important for the people doing animal or crop breeding. You can use it for analysis of incomplete block design. And mixed model is extremely good when you have missing data or when your design is unbalanced. You can use it for analysis of split plot. You can use it for analysis of repeated measure, and you can use it to handle any subsampling problem. And subsampling includes the use of pseudo replication or sampling from an experimental unit. We know that most of us are trained in the traditional analysis of variance, which belongs to a mixed model group. And yesterday I indicated that if you're dealing with a design experiment, then your statistical model will have two components. You have components that are related to the design factor effect, and then we have the component that is related to your treatment. And of course, you will have your error or the residual. So this is our model. You have things like block coming here. You have things like column coming here, row coming here, replicate coming here under the design. And then you have your treatment, whether it is a one factor or two factor or three factor and so on and so forth. Now, when you have more than one factor or one effect in your model, then you may start thinking about other mixed model approach. When we've done our analysis of variance, most of the assumptions that we make are related to the error terms. So under completely randomized design, the value that you observe can be explained by some general population mean, the effect of the treatment, and then you have your experimental error. So the experimental error for each observation will be there. And then if you're using randomized complete block design, you still have your general mean, you'll have the treatment effect, and then you'll also have the block effect, and then you have your random error, which is the noise. If you're using a Latin square design, then you still have this. You have the treatment, then you're blocking as two components. We have the column, and then we have the row. So as you can see from here, your model has a number of here we have 3 components. Here we have 4 components. Here we have 5 different components, and these are what we call our sources of variation. So most of the assumptions of analysis of variance are mainly related to the error terms and how these error terms are distributed and the variation that is associated with it. Of course, we summarize the assumption of analysis of variance under the term that the error terms, that is what we have seen. What we have seen here, these terms here, they should be random. That means they should not have pattern. They should be independent of each other, and they should have a normal distribution with a mean of 0 and common variance. And then if the assumption, any of the assumptions are violated, in our normal classes, we are taught that we can do transformation. So you can transform so that you take care of the independence of the observations. You can transform so that you make your data get normally distributed. But as we have progressed through the week, we looked at the logistic regressions or logic regression. We realized that you don't need your error term to be normally distributed. What you need is simply that you need to get a family of distribution that are there. So you move away from the normal linear model, you go to what we call a generalized linear models, where the assumption of normality is taken care of. And then the mixed model comes in, especially if you now have problem with the independence or the randomness of your error term. So the mixed model can come in and can handle the issue of dependency. And please note that with the mixed model, the linear mixed model, you also still maintain the assumptions of normality of the residual, but you can progress and do what we call generalized linear mixed model, where you can bring in different link functions, like by the logic function we saw from Susan and Ellen the other day. So you don't necessarily need to do data transformation. Data transformation means you're trying to force your data to follow a certain pattern, but you can decide to use an appropriate model for your data. That is now what we call the best strategy now. That means don't go and transform your data. Look for the best model for your that fits your data and do it. And then we looked at the error variances for the different levels or different blocks should be similar, and there should be no relationship between the error and that. Sorry, I forgot to tell you that we didn't start by asking you to present the results for now, for the assignment for now. We are going to bring that one later on. We want to first start this thing when everybody is fresh, and then later we can give you opportunity to share whatever you've done in the assignment. So we do recognize your effort, and we are not just going to take it for granted, please. So just hold on a little bit. We are going to give you time to show that. So the treatment effects in our model also, we assume that the treatment effects are fixed in that the treatments don't change or don't vary from trial to trial. So if I'm testing 3 different varieties, I expect that those effects will remain constant as you move. And we went ahead and then defined a few issues. So one of the assumptions we talked about is the independence. So here the experimental unit is supposed to receive treatment independent of each other. That is the design assumption. The implication in this case is that the different experimental units are independent of each other. The randomization that we looked at under experimental design takes care of if there is any pattern in the field that we are not sure of, we assume that a randomization will take care of that. But assumptions of analysis of variance is kind of ideal. When you go to the field, things are a little bit different. So if, for example, you're handling repeated measure, whether it is repeated over space or over time, we realize now that there will be some kind of correlation between observations, especially observation coming under a certain level. So we saw from Susan that you can take a measurement over time on one particular plot or one individual, one animal, and you as time progresses, the observation from time 1 are more related to observation from time 2, from time 3, and so on and so forth. And because of this one, this relationship between the different observations, the assumption of independence is now thrown out of the window. So what we need now, we need to take that into consideration when we are doing our data analysis. And that is where issue of mixed model comes in very handy. So there are also what we call clustered or data from nested or hierarchical design. So yesterday I demonstrated that you may be doing an on-farm trials. So in an on-farm trials, of course, you start by selecting maybe villages. You could have village number 1, village number 2, village number 3, and say village number 4. Is my volume very low? Are you getting me the right well? Okay. Okay, thank you. I will try to adjust accordingly. Okay, so from the village, of course, you go and select farmers or farms. So here I get my farm 1, farm 2, farm 3. Okay, and here you also get your different farms. Here you also get your different farms. Here you get your different farms. And then from the farms, maybe you get different plots. Okay. So this is what we call hierarchy. There are different hierarchy or there are different levels of nesting. So here, this kind of data is likely to have a correlation between observation taken between the within So you expect observation taken within the same farm to be more correlated compared to observation taken from another farm. So you can, if you are an animal scientist, you can look at piglets coming from the same sow as being related. If you're looking at randomized complete block design, you can assume that plots within a block are more related compared to plots within other blocks. If you're doing sociology, you can always talk about students in a class, in the same class being more related. Or in repeated measures, you can talk about taking data from the same individual that creates a correlation, or taking data over time, creating correlation. So yesterday we also said if we treat all observation as fully independent, then we are likely to overestimate the number of degrees of freedom. And the number of degrees of freedom is associated with the amount of information that you can extract from your data. So you tend to over-exaggerate the amount of information that you have from your data. Like yesterday, I told you that if we asked 10 people who have been attending this course to give us their opinion, I think by the time you are reaching the third person, most of the thing would have been said. So literally, the exact number of people who gives you the information is much less than 10. And that is how dependency actually rob you of the information. So those people who do spatial statistics or do geostatistics know the issue of spatial correlation and how that reduces the actual degrees of freedom of your test. So if this happens, then most likely you're going to wrongly reject the null hypothesis and it increases your type 1 error. So you're going to draw conclusion that there's a significant difference between observation or between treatments, while in actual case, there's no significant difference. So the hypothesis, the results of hypothesis testing is likely to be invalid and unreliable. So you're likely to draw a wrong conclusion, and this can have implication depending on what you're studying. If you're studying medicine, you may recommend drugs that may not work well because of the problem that there's the wrong assumption that you made about your data when doing the analysis. So how do we handle the violation of dependency in the data? So the typical analysis of variance assumes that the error terms are independent. I think Susan talks about the different error structure, the different structure. So here, for example, you assume that, let's say this is farm 1, farm 2, farm 3, and farm number 4. So we have the same farm 1, farm 2, farm 3, 4. So of course, at the diagonal here, remember, if you are to calculate the covariance, so in the diagonal here you have the variance sigma square all the way. So now here we want to is there a relationship between number 1 and number 2? So you may have some kind of relation here. Now the analysis of variance assume that this relation is 0. So there's no relationship between 1 and 2, 1 and 3, and 1 and 4. So all these off diagonal elements will be 0. Okay. So that is the assumption that it makes. But if there is dependency, that means these values are not 0. These values have something else that we need to estimate. And then also went further and look at what we test, hypothesis testing and mixed model. So in the standard linear model that we are used to, the question that we are always interested in answering is there differences between treatments? Okay, so if you're comparing 3 different varieties, you want to ask yourself, are this variety different from each other? Does one particular variety perform better than another variety? That's the typical question that we are used to answering. But if you're a plant breeder or an animal breeder, for example, you're always interested also in the variation because in plant breeding or in animal breeding, we talk about genetic variation, genetic variance. All your ability to develop a new variety will depend on variation. If there's no variation, there is no improvement that we can make. So sometimes the interest may actually be in estimating variation rather than in testing for the different effect. Okay. So in this case, for example, you're not interested in testing which farm is the best. You're more interested, are there variation from one farm to the other? So the kind of hypothesis that we test under the mixed model is something that looks like this, that the farm effect is equal to 0, farm variation is equal to 0 versus farm variation not equal to 0. So in this case, the interest is in quantifying and comparing the level of variability at the different levels of the factors that you're studying. So you want to see, is there farm to farm variation? Is there village to village variation? Is there plot to plot variation? And as I indicated yesterday, let's say you want to set up an experiment on, let's say you want to, on 100 farms. So the question that you want, how do I distribute these farms? Do I pick very many villages, and how do I pick 100 villages and have one farm selected from each village? Or do I pick 10 villages and have 10 farms selected from each village? And that will now depend on the variation at the different levels. So when you're interested in quantifying variability at the different levels, then the kind of statistical model that you are going to use is not going to be the ordinary linear models. You're going to shift towards what we call the random effects model and then the mixed effects model. And that is the basis for what the presentation I'm trying to make now. So yesterday we went ahead and said, well, your model can be classified as fixed effect model, random effects model, and then the mixed effects model. And the assumption that we make about the nature of the effect of the factor that we are testing determine whether it is fixed, random, or mixed. So in the fixed model, like the traditional analysis of variance model, all the other factors that we are testing are considered to be fixed. The effect are considered to be fixed. The only effect that we consider to be random is the error. That is our experimental error variation. That is the only one that we consider to be random. On the other hand, for a random effects model, all the treatment effects will be considered to be random, while for the mixed model, we have both the random and the fixed effects in the same model. So in this case, our interest would be to compare the fixed effects like variety, and then our interest is also to estimate the variation in the level of the random factors. So that's where the mixed model comes in quite handy. For those ones who have done some work in let's say those who do quantitative QTL analysis, you hear people talk about BLUP and talking about BLUE. So those are associated with the random and the fixed effect. So you need to be able to differentiate what they are so that you choose the appropriate estimate for your analysis. So the linear models or the fixed effects model consider all the factors to be fixed. And I gave you yesterday this table. I gave you summary step, but anyway, let me first go through this, then I can come back there. So here, for all the levels of factors in the experiments are predetermined. And then the inference are only for those levels of factor included in the experiment. So your inference is going to be restricted. If it is 3 variety, is going to be restricted to 3 varieties. So the researcher wants to compare these specific levels of factors. So that means they should be chosen because of specific interest, some uniqueness in them that you cannot get in other sets of treatment. So if you have variety that are resistant to a certain pest, that would be unique to it, and you would want to see whether that uniqueness actually gives it advantage over what the farmers currently grow. Okay, so the examples of factors which effects can be considered to be fixed include sets of varieties, maybe drugs that are tested on human beings or animals, or could also be things like fertilizers and so on and so forth. Then we went ahead and look at this example here. So here, suppose we want to evaluate the performance of new varieties in a given agroecological zone. So the possible, of course, it depends on your research objectives. So a possible experiment could consist of, say, new varieties. We have 2 new varieties and we want to compare with a local check. So if you don't know agriculture maths, the local check is we can take it as the variety that the farmers are already growing. So you want to compare anything new with what already exists in the environment. So of course we have to compare these varieties on the farmer's field. So let's say we select a number of farms, say 10 farms, and then we test the 3 variety in within each of the farm. And then of course we need to measure our yield, dry matter, plant height, and so on and so forth. So now when we comes to issue of analysis, then we need to specify which of our factors are considered to be fixed and which of our factors considered to be random. So here, the interest is clearly only on those 2 new varieties plus the local check. So we would rightly classify variety as having a fixed effect. But for the case of the farms, is a bit tricky. So you need to ask yourself a few questions. So the first thing is, if the interest is only on those 10 farms, let's say those 10 farms are a special kind of farms. Maybe one of the farms is on the island, another one is that. Then we would consider those farms to be fixed. If not, if the 10 farms are just to represent a larger population of farms, then the best thing to do would be to consider a farm as a random factor. So, and yesterday I went ahead and said, well, you need to ask this question here. Can I address the same research question using another set of factors? In this case, can I achieve the same, answer the same research question using another set of 10 farms? If the answer is yes, then the farm is a random effect. If the answer is no, then you can treat the farm as a fixed effect. Okay, then I showed you this table, which I'm not going to go through now, probably. Okay, so just to recap again on random effect. So usually random effects are just a way to introduce an extra source of variation. So structure dependency between observation can be handled. So you want to introduce an extra source of variation in your model. So what we can say is that if I have a model, let's say I have a model which is the mean plus the effect of the variety and then plus error. So this can be my normal. So if I now say, okay, I want to bring in farm also in my model. So then I have this part here, plus the variety, plus farm, plus error. So now by introducing farm as a random factor in my model, so what I'm actually saying now that I'm going to model my data in such a way that plots that are coming from the same farm will have some correlation. So if I come back to our variance covariance matrix that we talked about earlier on, so if we have farm 1 farm 1 on both sides, farm 2. Okay, let's say plot 1, plot 2, plot 3, plot 1, 2, and 3. So if plot 1 and 2 are from the same farm, that means they will have some correlation here. The correlation will no longer be 0. But if farm 1 and farm 3 are from different farms, so let's say this value could be 0.2. And then if one is different, one is in a different farm 3, then we can assume that this correlation is equal to 0. So of course, this will be the variance sigma square. So this is now what we are going to introduce into our model, and we are going to use this to do our data analysis. So by introducing a random factor into the model, you're actually now telling your analysis package that please consider data observation coming from this level to be related, and we can later on estimate the relationship by determining the correlation at either farm level or plot level or village level, as we're going to see from our example. So they represent a layer of some kind of a nuisance factor. These are factors that we are not interested in estimating their effect, but we want to take care of their variation. So for example, of a random can be block, can be litter. We saw in analysis of split plot and in the analysis of incomplete block design that we actually use a block. So the blocks are kind of a nuisance factor. We are not interested in determining which block is the best. We are interested in determining, can we remove the effect of the block before we can compare our treatment? So although here we talk of blocks of random effect as being a nuisance in our analysis, but some cases we are actually interested in the random effects in themselves. So I told you yesterday that the animals and plant breeders are very much interested in estimating the breeding value of an individual. So if you have a bull, you want to determine what's the breeding value of this particular bull. Can I keep this bull for my future breeding? And that is simply the expected value of the offsprings of that particular bull. So you can use the mixed model to determine the breeding value of a sire, which is, I think, animal scientists understand this language better. And this is where we are going to look at what we call best linear unbiased predictor from the random effect. While for the fixed effect, we have what we call BLUP, a best linear unbiased estimator. Okay, so that was where we ended yesterday. And somehow I didn't want to start the day with I don't like starting the day with the formulas, because that will be bad. That's why I wanted you guys to be fresh, then we can start looking at the formulas. So the first thing is, formulas are not meant to harden your life. It's actually meant to make your life easy. So if you can learn the formulas, then you can make life a lot easier. I know in most cases it can make you dream. I remember when I first went to do masters in applied statistics after doing agriculture. Yeah, I used to dream about chi-squares and what in the first week. So it was really, I understand if you start dreaming about these letters. Yeah. Now, so I'm going to introduce the some equations. They're not there to kill you. So we're going to go over it very slowly, and then we try to appreciate and understand. Now, why it's important to understand this is because if you want to do programming like you're doing in R, you actually need to have some basic understanding of what is going on. Okay, so we are going to start with a linear model, the model that we know. So with a linear model, you have, this is the response variable. So this can be yield from your plot. And then here we have some kind of a constant, the overall mean of the experiment. This is the effect of, say, let's say this is the effect of variety. This is the effect of the farm. And then this is the interaction between the farm and the variety. And then this is our error term. This is our experimental error. Now, the assumption about the experimental error is that it has a normal distribution with some variance sigma square. This is statistician love this IID. So it's IID, independent, identically independently distributed as a normal distribution. So here it's important to look at, so we're saying I, J, and K. So I is from treatment I, from block J, and then K is it stands for the number of replication, okay? So in our regression, as we are in our model, like the one presented the other day by Susan, we have what we call the intercept, which is in this case is our overall mean. Then we have the effect of the variety, we have the effect of the farm, and then we have the interaction. Now, all these factors here in the linear models, they are we consider their effects to be fixed. That means we are going to compare varieties, we are going to compare farms, and then we are going to compare combinations of varieties and farms. So that is what it means here. So the hypothesis, our hypothesis will be related to the mean. So here, for example, can say that the mean of variety 1 is the same as the mean of variety 2, the mean of variety 3, and so on and so forth. For farm, our interest would be saying the mean of farm 1 is the same as the mean for farm 2, and so on and so forth. And then for the interaction, we are testing whether the performance of variety is consistent over the different farms or the different level. Now, this is where the issue of the farm now becomes controversial. That, okay, now if you're going to test and tell us that this is the best farm, so the question is then what? What do we do with that information? But if you tell us that this is the best variety, then you can tell farmers that, please, actually you adopt this variety because it gives you a better yield compared to the other thing. So the most useful information you probably want about a farm would be farm to farm variation to help you actually in handling your varieties next time if you want to do any analysis. So the residual has its own uniqueness. It's in this case we assume that it comes from a normal distribution. It has a constant variance, and then there's independency of the variance. Don't depend on the mean, or don't depend on the treatment, don't depend on the block. Like we talk about, this is IID normal, IID, that is identically independently distributed. In our case, the distribution that we are talking about is a normal distribution. Now we're using a linear model because we assume it's a normal distribution. Now, if this distribution changes to say a binomial distribution or Poisson distribution, then we're going to use the model that Ellen talked about, the generalized linear models that you have. So we also have, so from the general linear model, we can actually progress to the generalized linear models. So in the linear model, the only factor that is random is the error. The only thing that's random is error, because that's the assumption that we have. And then the residual, this term here, is the variation between unit. Any other variation that we cannot explain by treatment or by farm or by what is what we call our experimental error, which is our residue. I think I talked about this one quite well when you're talking about experimental design. Okay. So by residual being independent, what do we mean? We means the correlation or the covariance is equal to 0. The correlation between any two residual should be equal to 0. Okay. Maybe let me see what I can. How many people are comfortable with with calculating covariance and correlation? Can I see some yeses around on no's? Somehow. Okay. I think I've seen what I want to see now. Okay. So when we are talking about linear, when we are talking about regression, I think Susan talked about correlation. So correlation measures relationship between different linear relationship between two variables. So let's say, for example, we have here, let's say here we have, let's say here we have the size of your head. And then here we have your weight. Okay. So what we do, we are going to weigh your body. You're going to give us your weight, and then you're also going to determine the size of your head. Now, if we have this relationship, let's say this is the Madame Ellen. She has a small head. She also has a small weight. Okay. And then this is me now. I have a big head and a big weight. And Susan is somewhere in the middle, yeah. So, and some of you are going to be somewhere here like that. Okay, so what we have here is we can actually see now that there seems to be some kind of a straight relationship here. So if the bigger the size of your head, the heavier you are. So we can actually come up with a regression model that we can just look at your head and we can predict how heavy you are. Okay, that would be something that we can do. So what we are talking about here is that if I have here, instead of, let me just clean it up and then I start. I'm going to change this a little bit. Okay, so let's say here I have error term. This is the residual now, residual ij, and this is also residual. So let's say this is the first residual from plot 1. This is so this residual 1, residual 2, residual 3, residual 4, 5, 6. We are plotting it like you're plotting one residual against the others. So if you see some, I mean, you want to see, are they related? So because residuals are because these are literally supposed to be noise, so you would not want to see some kind of relationship. So that's why when we say the covariance between the first error and the second error should be equal to 0. That there should be no relationship for all the i's and all the j's and all the k's. Okay, so so what we're saying is that observation error from observation 1, from treatment 1, from replication 1 should have no relationship with the second error from the same observation, error 1, 1, 2. Okay, so the same treatment and then different replicates. So there should be no relation here. That's why we're saying the correlation is equal to 0. And covariance equal to 0. From the covariance, you calculate the correlation. So the covariance is the correlation is simply the covariance divided by the square root of the product of the square root of the two variances. So this is the assumption that we make in our analysis of the linear model, that to sum it up, we are saying that each error is not related to any other error. Okay, and in terms of matrices, this is what you have. So we are saying the correlation, the whole of this area here is zeros. So let's say this is 1, 2, 3, 4, 5. This is also 1, 2, 3, 4. Okay, and 5. So this is plot number 1. So plot number 1 is not related to plot number 2. Plot number 1 is not related to plot number 3. Plot number 1 is not related to plot number 4, is not related to plot number 5. Plot number 2 is not related to number 3, is not. So the all of this area here should have zeros only. Okay? All of these areas here should also have zeros only. Okay? The only thing that we have here is this, and this is our variance. So, and this is what we call, this is our variance covariance matrix. Okay. So here you have the variances along the diagonal, and then you have covariances or correlation along the off diagonal. So in terms of this is how we wrote our, clean up here. Okay. So this is how we wrote our model, a single value. But we can combine all this one here into a matrix to make life a lot easier. So let me just try to make it more palatable. So let's say this is observation 1. Let me do it here. So let's say I have observation number 1, treatment 1, variety 1 from field 1, the first replicate. So this one is going to be equal to the mean, overall mean, plus the effect of treatment 1, plus the effect of farm 1, okay, plus the interaction, that is alpha and beta for farm 1, 1, and then we have residual for 1, 1, 1, 3 ones. So we have written this here, this equation here for the first plot. We are going to write it again for the second plot. The second plot is still coming from the same variety, same farm, but this is now the second replication. So here you have your mu is still the same treatment, the same variety, so it's still 1. It's still the same farm, so this one then becomes number, it's still 1. And then it's also still the same farm and same varieties. So this alpha, beta, 1, 1. The only difference here is now that this is the second error. You have 1, 1, 2. Okay. So we can go to, let's say, treatment variety 2, farm 1, variety 2, farm 1, replicate number 1. So this one will move. So this one you'll have your mu plus. So now we are changing alpha, now changes to 2. Okay. The farm is still 1. So we still have B1. And then the interaction now changes to beta. So it becomes now 2, 1. And then this one here become 2, 1, 1. Okay. So we can have this. If you have 20 plots, you will need to have for each of the 20 plots. Now it is easier to write this in forms of a matrix and a vector. So we can create one vector for all the y's. So you have your y 1, 1, 1, y 1, 1, 2, you have it all up to down here. And then this one here is what, if it is written y with underline here, so this is a vector. So we're saying now, instead of writing each one, for each one is separately, we combine them together to create a vector. The next one that we are going to do, then we are going to also combine the other part also into, this time we are going to have a matrix. So we are going to have a matrix that has 1, 1, 1, 1, 1, 1 here, to stand for this value here, because all of them have the mean. And then, so this is going to be the mean. And then the next one is going to be alpha 1. Then you have alpha 2 for field 2, and so on and so forth. So we are going to convert this, and so that is why we have this. So we can write it in this way. So this is our vector. That is all the response variable into one vector. And then this is going to be what we call the design matrix. So the design matrix is simply a matrix that has ones and zeros to show us where the observation fall. Does it fall on replicate? Does it fall on replicate number 1? Does it fall on variety 1? Does it fall on 1? So it's on farm 1. So you're going to have, let me just have it here a little bit. So okay, so this one here is what I have as y11, like this. This is that. The next one is, I need this one here. So this is where I'm going to have something like this. I want to have a line for mu. I want to have a line for variety 1. I want to have line for variety 2. I want to have line for farm 1. I want to have line for farm 2. And then I want to have variety 1, farm 1. And then variety 1, farm 2. And then so 1, 1, 1, 2, and then I have 2, 1, and so variety 2, farm 1, and then variety 2, farm 2. So this is going to be a matrix. So here then, when I come to my number 1, they all have the mean. So this is going to be a line 1, 1, 1. Now the first two varieties have, the first two plots are for variety 1. So I'm going to have 1 here. I'm going to have 1 there. The rest are all going to be zeros. And then the first two don't have, the first two blocks, the first two plots don't have variety 2. The first two are on farm 1, and then they are not on farm 2. And then here, 1, 1, so there's 1 here. Here is also 1, 1, so there's 1 here. The rest will all be zeros. So there's no 1, 2, so this is 0, this is 0, and that is 0. So you have ones and zeros. So the matrix that we have here, I'm going to remove what is on top now. And then to complete, I'm going to have another vector here, but this is now the vector of my parameters, the beta. So this is where you have your one, your mu1. You have your alpha 1, alpha 2. So that I can now get, if I multiply this line here with this one here, I get back my equation here, this equation here. I can get that equation there, I can get that equation there. So this is the what we call a matrix representation of the model that we have. So the matrix representation of the model okay. So this is our vector and this is our design matrix. It has ones and zeros. And then this is the vector of fixed effects. So our fixed effects are alpha and betas. And then this one here is now showing us the distribution of the error term. So what this is also vector of E11, 111 up to that one. So this is a vector here. And then the variance in this case is also now looking at this. So this is the variance. That's why I said is I times R times sigma square I. I is simply a vector, is a matrix where you have ones in the diagonal and zero elsewhere. So that's why if you multiply sigma square with that, you're going to get this because all the rest will be equal to zero. So this is what we call the variance covariance matrix. For it is very, it's for a linear model, it is simple. But for a mixed model, it gets a little bit complicated, but you don't need to worry about that because the computer will do for you all the calculations and what. So what you simply need to do is you need to know how these things move. So can I see, are you, can't see what is happening below? So can we see, can I find out whether you got you understood the matrix notation for the model? There's one yes. Okay, good. Okay, so I think we are doing great. Somehow you'll get good. So that's fine. I'm off now. Okay. So what we wanted, this is a vector that has all the fixed effects. This is what we call a design matrix. So a design matrix is a matrix that shows where each observation comes from in terms of, does it come from a plot with the treatment A, with the treatment B, from where? That is what you have there. And then the next one is the vector of residual. And then we have R, which is the variance covariance matrix of the data given R, given by vector by a matrix R. So what we see from here is that the variance is the same for all observations. So all the observations have the same variance. The observations are independent because there is no correlation. The correlation is zero, or the covariance is zero. So remember, if the covariance equal to zero implies there's no correlation, that means there's independent. Now, what happens sometimes is that these variances may actually be different. Remember, one of the assumptions of analysis of variance is homogeneity of variance. So homogeneity of variance means you need to have the variance here constant. Okay, but if this variance is different from that variance, is different from that variance, then analysis of variance will not be able to help you anymore. And that's why you go in for transformation. The good news is that if you're using a mixed model, you can actually specify you can actually specify the different variances that you want to use for your analysis, and it will be done without any problem. The computers have a lot of power now, so you will not have any challenge with that. So this is just a representation that I was trying to struggle with. So you can see here that if this is the mu, this is our alpha 1. This is, so you move here. So let's say in this case, we have 3 varieties. So alpha 1, alpha 2, and alpha 3. So the first column here will be the overall mean. The second column will be telling us whether you have treatment 1 or treatment. So here you can see the first observation as treatment 1, variety 1. The second one also has variety 1. And then the third one now has variety 2. So this one will be 0 here. So the rest now will be zeros. You have zeros here, up to down. So what we're saying is that because the total number of observation in this case is 60. Remember, we have 3 varieties. Each variety has 2 plots on a farm. So there are 6 plots for the same variety on a farm, and then there are 10 farms. So you have here, there are 60 of them. So this is 60 by 1. So 1 means we have only one column and we have 60 rows. Now, when it comes to this matrix X, when you come to matrix X, with matrix X, we have one parameter for the intercept, the mu. So this is for the mu. And then we have 3 varieties. So we have alpha 1, alpha 2, and alpha 3. Okay. And then we have 10 farms. So the effect of 10 farms. So you have farm 1 up to farm number 10. So that means you have 3 plus 10, that is 13 plus 1, that is 44. That is not 14. So here you have 1 for mu. You have 3 for varieties, that is 4. You have 10 for farms, that is 14. And then for the combination, remember here you have 3 variety by 10 farms. So you have 10 combination to giving you 30. So you have 30. So that's why this, the number of columns here is 44, and then the number of rows is 66 because you have these 66 observations. Then here you have 44 by 1 because when you're going to multiply this with that so that we can generate our model. And then here you have 60 by 1 because each of the observation here will have a residual. And then this one here will also be a 60 by 60 matrix with the sigma square on the diagonal and zeros off the diagonal. So this is the interpretation of the model. This is a fixed effects model. Now the thing is coming back. Okay, so this is what I was trying to do. There's mu. There are 3 of these. There are 10 of these, and there are 30 of these. So giving us the 44. And then here you know how we got the 60. So 1 plus 3 plus 10 plus 30 gives you the 44. And then when you want to generate back your model, so for 1, 1, 1, remember here, you have 1 for everybody. So 1 times mu plus 1 times alpha 1, because the first one is on variety 1, plus 0 times 2, because it's not on variety 2, plus, so will be 0 for 2 and 3 varieties. And then you'll, for farm, it will be farm 1 with, so here you have for farm 1, and then you also have for the interaction between farm 1 and variety 1, and then you have your 1, 1, 1. So you need to produce this for 1, 2, 1, 1, 2, 3, and so on and so forth. So that is the representation of our model. Okay, so okay, so that is how the mixed model will look like. So the fixed effects model will look like, we have only one component here. We have this, which this takes care of the fixed, and then we have only one error term which takes care of it. So these are fixed, this is random. Now, so, but for the random model, here, so if we decided to take farm as random, farm effects as random, then we have a different model. So the intercept remain fixed, the variety remain fixed. Now we have assumed that the farm effect is random, and then, so if the farm effect is random, any interaction between a random and a fixed effect will be random. So the effect of variety times the effect of the farm is also random, and then the error is random. So the one in red are random effect, the one in blue are fixed effect. So now in this case, now we have a mixed model because we have the fixed effect and then we have the random effect in the same model. Okay, because of the assumption that we have made in relation to that. Okay, somebody is posting a reference for a book on matrices. Please, you need to read that to be sure that you get this right. So the rule is that the interaction between a fixed and a random factor is always random. So a linear mixed model combines fixed and random factor so that some of the factors in the experiments are predetermined, like our fixed effect, like the variety, and at least one of the factors have a random selection of levels. So here you have at least 2 or more random terms. Remember, the error is already a random term that is present in the linear model, in the fixed effects model. So you need an additional factor to make it a mixed model. So the inclusion of 2 or more random term automatically introduces correlation between the observations, as I already explained. Okay, now one thing I want you to note here, this is just for notation purposes. When you're writing a model, the fixed effects are written with Greek letters. That is by convention. And then the random effects by written with in alphabetical, the ordinary alphabetical letters. That's why here we change from beta to B. For the fixed effect, this is beta. For the random effect, this is B. Okay, so here then we have our mixed model now. These 2 are fixed, and then these 3 are random. Okay, now remember, now the randoms comes from a distribution. So here we say B is IID normal with a mean of 0 and variance sigma square B. So this is now the variance between the B, and this is related to the correlation that you're going to impose on the observation that comes from the level B. And then the A by B interaction is also having IID normal with mean of 0 and variance of sigma square AB, and then of course our error also has IID normal with 0 and sigma square. Okay, so note that if we specify a distribution for each of the, note that we specify a distribution for each of the random terms in our model. So the farm effect, it has a distribution. The farm by variety effect, it has a distribution. The residual, it has a distribution. But the fixed effects are estimated, so they don't come from a distribution. If you go back to my table here, this is what I talked about here, that the fixed effect assume a non-fixed quantity, while a random effect is a realization of a random variable. So it comes from a distribution, a sum distribution, while this one here takes on any value in the range from negative infinity to positive infinity. I think the harder part is gone now. Okay, so in addition to, remember our fixed effect, at this, we have x beta plus e. That was our fixed effects model. Now our mixed effect model now has an additional component. So this is still our fixed effect. This is now our random effect, and this is our error. Okay. So remember, E has a distribution, and then U also has a distribution. But now we are looking at U now as a vector of all the fixed effects. So U has a normal distribution with this 0 now is a vector of 0, 0, 0, 0, and then this G now is a matrix. And that matrix now will have your sigma something along here, and then it will also tell you whether there is correlation or not. And the correlation now will depend on the value that we assign to that. So X is our design matrix for fixed effect. B is the vector of fixed effect. Z is the design matrix for random effect, and U is a vector for random effect. And then our E is a vector of residual. So the variance covariance parameter now comes in two matrices, in matrix G for this part here and matrix R for that part there. So that is the matrix notation for linear mixed model. I would request you go watch some YouTube about mixed model so that you understand this thing a lot better. So now, instead of having all the 44 together, now we've broken up them into two. So remember here we have the fixed part, which is, this is the first column for the mean. This is for variety 1. Then you have for variety 2. And then you have for variety 3. Okay. So here you have 1, 1. The rest will all be zeros because they're not appearing there. So you have zeros, you have zeros, you have zeros, and then you have 1. So then at the end of the day, we can multiply this with this to get us that, because you'll have mu times 1 plus 1 here times alpha 1, and then will be 0 times alpha 2, and so on and so forth. That will generate. And then the design matrix for the random part is this one here. And then the vector for the random part is that. And then the vector for the residue is that. Now, when we estimate this, the estimates of U, these are our prediction that the BLUP comes from these particular terms here. So here you still have a total of 60 observation. The fixed parameters include the mean, the intercept, and then the effect of the 3 varieties. The random effect contained the effect of the 10 farms and interaction between the 10 farms and the 3 variety to give us a total of 40. So you have 40 effects. You have 44 for fixed. So you see now in this case, you still, I mean, you still have 60 by 44. That means you're still okay. You still have, you're not overfitting your model. Check what is in the chat, what is going on. Okay, so this is our parameterization of the mixed model. Okay, now there are going to be only 3 art slides. The rest are going to be very easy now. So just tighten your belt a little bit. And what is overfitting? Now, if you overfit a model, means you see the best thing. Okay, let me do it like this. You see, when you collect data from, say, 10 individuals, for example. You can fit one model that will be used by the 10 individuals. But the best model would be that each person's data is its best model. But that means you have 10 different models for each of the persons. So you can, that's what I say, you can overfit the data in that case. But we are not going to discuss that for now. Please, let's close our eyes a little bit and try to imagine these numbers running around, and we see what is going to happen. So we want to look at our fixed effect model. Okay, so remember here, the fixed effect. So I'm going to have let me just have 2 values. Let's say I look for observation from variety 1. Plot, okay, variety 1, first observation from variety 1, plot 1, and on farm 1. Okay, this one I give it as mu plus alpha 1 plus beta 1 plus alpha beta 1 plus error 1 1 1. We're just substituting the values in our model here. We can also do for observation number 2, which is 1 1 2. So this is going to be equal to we have the first, that is the intercept, the mean. We are still dealing with the same variety, so alpha is still 1. We are dealing with the same farm still, so beta is also 1. And then the interaction is also 1 1. That is what we have here, alpha 1 1. But now the error is different because we are now in the second observation. So plus E 1 1 1. Okay. Now, if I want to get the correlation, let's say I want to get the covariance between the first 2 observations. So I want to get covariance between 1 1 1 1 and covariance between 1 1 2. Okay. Of course, this is the same as I can substitute my values of y 1 1 and y 2 2 from the equation. So that means I can have my mu plus alpha 1 plus beta 1 plus alpha beta alpha beta 1 1 plus E 1 1 1 1 1 1, and then I'm having it covariant with mu plus alpha 1, because in the second one is also the same variety still, plus beta 1 is the same field still. Oh, now it's getting more crazy. Plus alpha beta 1 1 you can't see the downer one. Okay, I'm going to okay. Let me use the Word document, then discard. So let me share again. And I can type now, it's seen. But in PowerPoint, no, then I can't type on it. Okay, so we are looking at the covariance between y 1 1 1 and y 1 1 2. Okay, we can say these ones are supposed to go down a bit. Okay, but remember our y 1 1 1 is but the pen is the one I'm using and making that. So, so you're taking me back to where? So here I have my mu plus variety 1, let's say V1 effect plus farm 1 effect plus interaction, that is V1 farm 1 1 1 effect plus error 1 1. So 1 1 1. So that's what I have here. Let me make this one down a bit. And then for 2, we can have more or less similar thing. We only change the last one. So this becomes the 2. So as you see from here is replicate. So let's say this is the 2 coming there. So here we have 1 1, first variety, first field, first replicate, first variety, first field, second replicate. So now my correlation now then becomes the covariance, not correlation. So it's the covariance of these 2 values here. So is that clear? Because I want, before I go into I want to show how I moved away from y111, y112 to mu and all that. If that does look okay, then I can proceed. I can go back to my slide. Okay, good. Okay, so what I've done here, I've simply got this as my y111, and then this as my y111. Okay, I want to ask a question. Does something which is fixed vary, change in value? Does something constant change in value? No. Okay, so the fixed effects don't change. They are supposed to be the same. So if you're talking about covariance, then they fall off. So these ones here, because we said they're fixed, so this one are not there. They completely change off. This one change off. Okay, so our covariance now has only gone to this. Remember, we have this one remaining. It's only this and this, because these are variable, therefore they can come into covariance. So the covariance between any two observations is equal to the covariance of their errors. Okay, and remember in the ANOVA we said the covariance of the error is 0. So in a mixed model, the covariance between any two observations is equal to 0. Okay, so the only source of variation, as we say, is in the error. So there's no correlation, and the independent between observation. But if we have more than one source of variation, then the correlation is not going to be 0, it's going to be more than 0. Okay, so now we are changing now, we are assuming now that, so we assume that these two now are the only one which are fixed. These two are fixed. Okay, so we can get rid of them. Then we move to the next step now. You see now these are now P is the effect of the farm is variable. AB is the interaction between farm and variety is variable. And then the E is also variable. So now we have, so we can change this, for example, if you manipulate this a little bit, will then bring you back to the covariance between the farm effects, the covariance between the interaction between the farm effects, and then the covariance between the error terms. Those are now where we've ended up with if we are dealing with a mixed model. Okay. So we can have a situation like this. So here we have J and J prime. So let's say, for example, if you're dealing with the same farm. So the same farm, that means we could have something like this, covariance between B1, B and B. Let's say B1 and B1. Okay, so this then would be the covariance. If it is the same variety, if A is the same as B, you will have that. So let me just first go down a bit and then I'll come back and do the explanation. Okay, so here, if Bj is the same as Bj prime, then we are dealing with the same farm. Okay, so for farm 1, we will have, okay, I'm too fast. Okay, so okay, let me go back here and start. So we have here two components. We have the components that are fixed. Remember this, the variety effect, we assume it as a fixed effect. Of course, the intercept is a fixed effect. So this is our fixed effect. And then this is also another fixed effect. So since we are looking at covariation, we say fixed effects or constant don't vary. So they can actually move away from our model. So we remove them. Okay. So the next thing that remain there for that, you will have this, which is random, this, which is random, that, which is random, this, which is random, random, and random. Okay. So we are moved from this to this set, this level here now. So we have Bj plus ABij plus EIJK. And then for the other one, you'll have Bj prime AB, I prime J prime, and then that. So let me just put these numbers to the J and the one. So let's say, for example, that J is equal to 1, and then J prime is equal to 2. Let's just put the number here so that we can see what happens here. So here, and then let's say I is equal to 1 also. And then I prime is equal to say 2. Okay. So what will happen would be that we have this covariance here. So where there is a J, we're going to replace with 1. So here you have B1 and B2, because we say J prime is equal to 2. Okay. So this is the covariance between farm 1 and farm 2. That's a block between a plot on farm 1 and a plot on farm 2. Okay. Then we go here and we look at the other ones as well. Okay. So where there is I, we put 1. Where there is J, we put 1. Where there's I prime, we put 2. Where there's J prime, we put 2. So this one will be alpha B 1 1. Okay. So we're saying variety 1 on farm 1, and then we are putting at variety 2 on farm 2. Let me get. Okay, 2 2. Okay, so in this case, then we'll be say what is the relationship between a plot. There's a plot on farm 1, and then a plot on farm. Okay, no, a plot on farm a plot on farm 1 and a plot on farm 2, and then here you have a plot on farm 1 having variety 1 with a plot on farm 2 having variety 2. So this is what will give us the relationship that we are looking at, because we need this to put into our model. In our model, to put it here, if this relationship. Remember, we have 60 observations, so we need to relate them. How do they relate to each other? Some relationship will be 0, some relationship will not be 0. Okay. So are we okay now from there? because somebody said I was very fast. So can I assume that I've slowed down a bit? I have to do everything possible to make sure that today is a good day, because you sacrifice your weekend. So we also need to do everything possible. Okay, good. Okay, so I'm going to wrap off this a bit and then I start again. Okay, so here what we're saying is that the B and AB random effects are potential source of covariation. Okay, when B and AB are the same, at the same level. So like if you have variety 1, plot 1 and variety 1 plot 2 on the same farm, then everything here will be 1, 1. Okay, so here I'll have B1 plus alpha beta 1, 1 and then alpha beta. Okay, and then of course you have your error also there. So this would be the relationship that I have. So if B is equal to J is equal to J prime, so that means you're on the same in the same plot. Now, if BJ is also equal to BJ prime, that's if you are on the, so the first thing is we have to be on the same farm. You can be on the same farm, but you have different varieties. Two plots can be on the same farm, we'd have different varieties. Okay, so here the same farm, you would share this. You have B1, okay? And then if you're on the same farm and you share the same variety, then your relationship is going to be a little bit more tighter. The fact that you're on the same farm makes you related, plus the fact that you are the same variety. So you'd expect plots that are occurring in the same farm and having the same variety are supposed to be more correlated than having different varieties. Okay, and then you could also be that you are completely on different farms. So you can be on the same farm. Two plots can be on the same farm. So let's say I have here. Let me just draw here. I have farm 1, and I have 3 plots here on this farm here. This is my farm 2 with 3 plots also on the same. Okay. Now, if there is variety 1 here and variety 1 there, okay, and let's say here I have variety 2, okay. So these 2 plots, the observation I'm going to get from these 2 plots are related for 2 reasons. The first reason is that the 2 plots are on the same farm. The second reason is that the 2 plots are having the same variety. Now, if I have here my V2, V1 and plot this plot and this plot, let me say this is plot number 1, plot number 2, and plot number 3. Now, plot number 1 and plot number 3 are only related by the fact that they're on the same farm. But plot number 1 and plot number 2 are related by 2 facts. The first fact is that they're on the same farm, and then the second one is that they share the same variety. So here you have the same variety, but on different farms. So if there's any relationship, then they don't share any relationship because variety is fixed. So you expect variety here and variety there to have fixed. There's no variation there. So this is the basis for which we are going to define relationship in a mixed model. And this is how the correlation is in a mixed model is going to be calculated. I'll proceed a little bit, and if there's need be, I'll come back. Okay. Okay, so here, if you have, so in this case, let's say, for example, we have observation from two different farms. That is when J is not equal to J prime. Thank you. I have some question that I need to ask to answer. Say, give an example how fixed effects and random effects can be used in modeling. Can we use mixed model when we use Likert scale? When we have a research framework with mediating variable. Let's first get the facts right. Let's first get into the mixed model. Well, then we have those questions. I'll answer them at some point. Thank you. Keep the question coming. Now, this one is going to be very, very important. I'm going to be very, very slow here. Okay. So if let's say in this case, J is not equal to J prime. Okay, that is, we are in different farms. Okay, and also I is not equal to I prime. That is different varieties. Then there is no correlation. So if you have a plot a plot in Susan farm and a plot in Ellen's farm, they have different varieties. Those ones will not be related in any way. Their covariance will be equal to 0. Okay. Now, if you have J equals to J prime, okay, but I is not, J is supposed to be equal to, sorry. If J equals to J prime and but I is not equal to I prime. Okay. You have two plots on Susan's farm having different variety. Their relationship is only based on the fact that they share the same farm. Okay, that's their correlation or their covariance. Now, if you have J equals to J prime and I equals to I prime, same, you're on Susan's farm, two plots on Susan's farm, they're having the same variety. They are related because they're on the same farm, they're related because they share the same variety, so they have more relationship. So when you go back now to construct your variance covariance matrix, you have your sigma somewhere. So the relationship here now will depend on whether they are on different farm, different variety will be a 0. They're on different, the same farm, different variety, you have sigma square B as their covariance. And then if you're on the same farm, same variety, then you have sigma square B plus sigma square AB. So that would be the kind of relationship. So you can see in this case, it actually makes sense. If there are two plots that are on different farms, they have different variety, we assume they share nothing in common. If they are on the same farm but different variety, they share the same farm characteristics. And if they're on the same farm, same variety, they share both the farm characteristic and the combination of the farm and the variety characteristics. That's what would be what they will share. Okay, so I think the calculations are off almost. So the next thing is after this, then we're going to do some example, then we're going to run some scripts, and then we can release you for a weekend. Okay. Maybe some of you could have heard about the intra-class correlation. So here observations at the same level of random factor are correlated. That is what I've actually been trying to say. So for example, observation on varieties that share the same environments are calculated. If varieties share the same environment, they are correlated. Observation made on plot that share the same environment and share the same variety combination are even more correlated. Okay, and then we can visualize this using our matrix relation. I think I'll skip this. Okay, this is what I'm talking about here. So here I have my, so here is where you have the same farm and the same variety. This is the relationship that you'll enjoy there. So they're supposed to be a little bit more tighter. This is when they only share the same environment. And this is the error, our error term. And then this is our total variance. So our total variance is the variance due to the farm to farm variation, the variance due to the interaction between the variety and the farm, and then the variance due to the error variance. So these are the summaries that we have. So observations on plot that share the same environments are correlated, and then observation on plot sharing the same environment and same variety are even more correlated. So that's what I've demonstrated here. So we're also going to go through our, a few examples to show that. Okay, so the inference on mixed model. So remember, on mixed model there are two. We have the fixed effect model, and then we have the random effect model, and they all are looking at different aspects. So when it comes to the issue of statistical inference, we are going to be making inference differently. So the inference in the traditional linear models that are based mainly on, we can use either square estimation in the ANOVA, or we can use the method of maximum likelihood. So the least square method can also be used in linear mixed model, but only for special cases when we have balanced data. What is used mainly in the mixed model is what we call the restricted maximum likelihood, which is popularly known as REML. So this is actually very popular with the plant and animal breeders. Now this one here, somebody one time said, although ANOVA can do for you something, it's like you're still carrying your typewriter and moving around with it while other people have already gone. So I encourage you people to make sure you adopt the REML or the mixed model, not to go back to our old traditional method. It can still give you some I mean, you can type, of course, with the typewriter. That's fine. But then you may miss out on some bragging right. And there are some cases where your typewriter is not going to help you. Typewriter cannot save for you words and cannot do a lot of editing. I mean, you need to if you've seen the typewriter, you need to type a line over something, but here you can actually delete and can improve. So we need to go this way. I'm sure after today, we are going to go that way. Okay, so test of hypothesis. So fixed effect, we are interested in testing whether the effect of the treatments are equal to 0 or not, or whether the means are significantly different. So that is our test for fixed effect. And then for the random effect, we are testing whether the variance are equal to 0 versus where the variance are not equal to 0, greater than 0. Yeah, I would still want to emphasize here that the ANOVA approach can give you the same result as the mixed model approach if you're dealing with balanced data. But if you're dealing with data that is not balanced, then you're going to have it becomes a little bit of a challenging. The other thing also is that when you are dealing with the traditional analysis of variant approach, then if you want to calculate the variance associated with the different component, then you need to go through what we call the expected value. So you need to do some calculation mainly by hand, and then you still calculate and get the same value that REML would give you automatically. So I'm going to show you one example where we do the linear model analysis. After the linear model analysis, we calculate the expected the variances, and we compare with the variances that's calculated using the REML or using the mixed model approach. So in the past, there used to be lots of tables at the back of textbook that can be used to construct expected sums of squares. And using the expected sums of squares, we can actually calculate some variances if we assume that certain factors have random effects. So this is, for example, if you have two factors, you have factor A and factor B. Of course, if it is a factorial, that means you are interested in studying the interaction between factor A and factor B. Now, under the mixed model, the expected value for the different sums of squares is given here. So under the mixed model, expected value of error sums of squares, mean error sums of squares given as sigma square. And then let me show you one thing today, because today you've given up on everything. I'm going to show you some tricks today as a reward for being a very good student. When we are doing analysis of variance, we always calculate an F statistics. And we know from everywhere that you are taught that F statistics would be for A, would be it would be the mean sums of squares for A divided by the error sums of squares, that is MSE. That is what we teach our students. I believe my two colleagues also do the same thing. Now, of course, if we look here, okay, so let's put the formula up there. We have sigma square plus n under the fixed NB theta A, okay, over sigma square. That is from the expected value, okay? So now look here. Under the null hypothesis, we assume that mean sums of square A should actually be the same as mean sum square B. So under the null hypothesis, we assume that this value here is equal to 0. That's why you will have everything will be sigma square over sigma square. That should be equal to 1. Okay, so under the null hypothesis, when we see the effect of the treatment is equal to 0, that is when you know that the F calculated should be small, that is close to 1. If the F calculated is far away from 1, then you know that there's some effect here going on in this area here. Now, when the assumption is that one of the factors is random, things change completely. So this is for this column here. So it is okay. I can test for A, I can test for B because this will go away. I can test for AB, this will go away, and that will go away. So under the null hypothesis, this value here should actually be equal to that, should actually be equal to that, should actually be equal to that. But when we come to when we assume that is a mixed model, when we come to this one here, okay. So if I want to test for A, so F, so the upper one will be sigma square plus n sigma square AB plus NB theta sigma A. Okay, divide by sigma square. Okay, now first get my red pen now. Now you see, now even if we assume that this one is 0, these two will not be equal. So if you're going to use this MSE to test for this and that, you're going to get wrong results. If you assume that if your factors are random, if one of the factors is random, you're going to get wrong result. So the best way of testing these two would be to test using the interaction term. Okay, so if you test using the interaction term, then under the null hypothesis, you assume this effect is not there, so this will be the same as that, and then if this is not there, then that will be the same as that. So under the mix and under the fixed effect, you get different results. So if you assume that you have a mixed model and then you go and do the traditional analysis of variance, the F statistics that you're going to get for these two values will be wrong and is going to give you a wrong, you're going to draw a wrong conclusion from that. Okay, so here is okay. You can test this and that. If this is 0, then this should be close to 1. If that is 0, then this should be close to 1. That is 0, then this should be close to 1. You're okay. When it comes here, for you to test for A, you need to test with the interaction as your denominator, and then the degrees of freedom will also be the degrees of freedom of the interaction. So now from here now, there's no more calculation. We're just going to see some results. Let me see the time. Can we, you need a break? Can we have a 10 minutes break, please? Let's come back at 12:21. Okay, 12:25. I'm giving you 15 minutes. So we are starting soon. Mm, 2 more minutes, then we start. Okay, we are back, ladies and gentlemen. So this is just a simple example. So here we have analysis of variance table. We have variety, farm interactions, and then residual. So as we see from here, if all the effects are fixed, then we don't have any problem. But if we assume that the farm effect is random, that automatically will make also this one random. So then this test here will be wrong, because I already showed you from the other side, because what you need is then that to calculate a variance ratio here, you actually need to have the mean sums of squares for variety divide by the mean sums of square for the interaction, mean sums of squares for farm and variety, FV. So you need to calculate that. So that's why that one's wrong. I think we've already shown that. So forget about this, but I just want to show you here that you can still calculate the variance for B and for AB by making some kind of an equation here by so the beauty with the mixed model approach is that I don't need actually to do these simple calculations. But this calculation is simple only if you have a very simple design and you have a very balanced data. Once the data is not balanced, then definitely whatever you're going to come up with the calculation is not going to be not nearer to the truth. So what I'm going to do in one of example is that I'm going to calculate the variance components, of the variance component using the traditional analysis of variance, and then we are going to compare it with the one from the mixed model, and then we'll see that it is exactly the same. Only that in the mixed model, you don't need to do any calculation, everything else will be fine. So what you need to do in this case is simply you get the difference between AB and M, and then you divide by total number of observation, and then you get your values here. So I'm not going to emphasize this. I want us to go and do some practical. Of course, one of the area where mixed model becomes very advantageous is in the area where if you're doing plant animal, for example, your animal might die, your plots may get eaten up by goats or anything, the instrument may fail. But it could also be that when you're going to do experiment on the farmer's field, if it is animal science, the farmer may give you only a few animals, so you may not be able to have complete treatment on a farm. And in that case, the maximum likelihood becomes the most important method for the analysis. So the mixed model becomes very, very important. So the mixed model, we fit the mixed model using two methods. We have what we call the maximum likelihood method and then the residual maximum likelihood method. So with the maximum likelihood method, you have a set of parameters. So what you do with the maximum likelihood is just you look try to say, okay, given the data that I have, which parameter value will give me the most likely scenario? Like I said, if, for example, you go to a market and then you see vegetable all over the place. So you can ask yourself, what is the likelihood that I'm in a vegetarian market given what I see around? That's what maximum likelihood is all about. So these are the two methods that we use for estimating the variance components in our mixed model. The only difference between the maximum likelihood and residual maximum likelihood, REML, is that in REML, the data is used for the for fitting the model is after you remove the fixed effect. That's why I say it's residual. You first remove the fixed effects before you estimate the variance component. So REML likelihood is only a function of the variance parameter, not the fixed effect. So that somehow you need to be able to get a way of estimating the fixed effect and then using that fixed effect to estimate the variance component. So these days, what happens is then that we use the different iteration methods. I'm going to show you how it works. I remember somebody taught you that to calculate the variance, if you divide by n, we are told this is the population variance. If you divide by n minus 1, you are told that this is the sample variance. But today I'm going to tell you something slightly different, that the one that is divided by n is actually the maximum likelihood estimator, while the one that is divided by n minus 1 is the restricted maximum likelihood estimator. So the dividing by 1 is actually you estimated this particular parameter. So that means in your data, you're lacking one piece of information based on that. So this is what we call, this is unbiased. The value here, the estimate from REML is unbiased compared to the one from maximum likelihood. So in most cases, if you're interested in estimating the variance component, then we use the REML method. Please don't look at this. Okay, so what we're going to do now, I want us to change gear a little bit. We first go and do some calculations, and then I'll come back to wind up with this. So what I want us to do, I want us to change from me making the presentation to trying to run a few examples and then use this example to explain a few terms that we've been talking about. Okay, so can we get our R ready? So I'm going to change to R Studio. So can you get your R script ready? How many people have their R script ready to start running the program? Okay. So I'm going to do a bit of explanation. So I'm going to. So we need to call these libraries. So make sure you call the libraries. So let me zoom in a little bit. Okay. So we need a library for LMER test. This is where the one that has the mixed model. We need to run a few of this library like mass, CAS, Agricole, Malcolm, ggplot, Agridat, Lattice. Then you install a package called Faraway. And then we also call the package called Faraway. So can I see how many people have I've called the packages and I've installed the Faraway. I think Faraway is one of the packages that you still don't have. The Faraway package, we're going to use it for repeated measure. It's a data set for repeated measure that we're going to work on. Julius is done. Philip is done. Jen is done. Okay. So I have a small data set that came from a Latin square design experiment. We are just going to use it here just for illustration. It's not the right analysis to do, but I'm going to show you that it actually works. So what you need to do now is you first make sure that you set your working directory to where the data is. So I want you to set your working directory where you save the Latin square.csv data. At least by now, you should not be having any problem with that. So how many people have their data in the right place? Okay. So we need, once you have that, we need to run the Latin square data. So the first thing is we click. Now you see mine, I've got a red, and it's telling me cannot open the file. Latin square.csv, no such file or directory. So that means I did not specify my directory. So I need to do that. What you can do, you can go to session. You just look at what I'm trying to do if you're having a problem there. You go to session. You go to set working directory, and then you choose the working directory. So in my case, I'm going to just run it here. And then the next step, I should not have any problem running it. Yeah, so you can see now I have my data. So the first time I got a red because I did not specify my working directory. So it happens to everybody all the time. So don't feel bad if you see red. Red is okay. Shows that you're working. If you don't see red, then you might not be working. So we can first look at the structure of our data. So here tells you that there is a data frame, as you can see from there. There are 25 observations of 4 variables. We have row, we have column, we have treatment, and then we have yield. So it tells you row and column are integers. Then treatment are characters, and then yield are numeric. So what we need to do is we need to convert row, column, and treatment into factors. I think this one now you can do without any problem. So we can run, convert row, convert column, convert treatment. We can then check whether we are still okay, whether we have actually, the conversion has worked. So now we can see that the row is now a factor with 5 levels. The column is also a factor with 5 levels. Treatment is a factor with 5 levels. Remember, this is a Latin square design. So with the Latin square, the number of rows equals number of columns equals number of treatment. Okay. So with that, we are ready to do our analysis. Can we convert rows and columns to factors using one command? You can try, but for now, just do what we are doing here so that we don't waste time. That one you can try at your free time. Okay, Bernard, you can try that at your free time. That's fine. Okay, so the first thing that we want to do here is we want to run the first model. I call it model 0, model node. So in this model, I'm going to run the linear model. With this linear model, I have yield as my response variable. I have treatment as one of the factors. I have row and I have column. Now, all these ones, because it's a linear model, this is the fixed effect model. So the treatment is a fixed, row is fixed, and column is fixed. And then the data app I'm using is a Latin square design. Okay, so I can run this. Now I've also, you can run the same linear model using another command, AOV, like ANOVA. So now one of the function that I'm using early refused to accept the model built from LM. So later I shifted to building the same model with AOV. And then later for some comparison, I'll show you what happened. So we have built the first model. So what we can do, the first thing that we can do is we can check what this model is all about. What is it in the model? So let me first clean my console. So I can go and say ANOVA. So you can do this, ANOVA model 0. I click on that. Okay. So here we have the response is yield. The first source of variation is treatment. This is the sums of square for treatment, the mean sums of square for treatment, the F value for treatment, and this is our probability. And then the row, and then the column. So based on, I want to go to the chart, based on this result here, was there a need to use a Latin square in this experiment? Based on, assuming you are supposed to go back and do experiment in the same area, would you still use a Latin square or not? You give yes or no and tell me your answer. Would you still use a Latin square? Okay, I'm asking, look at this result here. This analysis of variance table here. So I'm asking questions that if you are to go back and do the carry out experiment in the same place, will you still use a Latin square? Yes or no? Please provide your answer. If it is yes, why? If it is no, why? Somebody said no, no significant effect of column. Okay, so as you see from here, the column effect seems not to be significant. So in telling you that your blocking with the column was probably not necessary. So if next time you're going back to the same area to do your experiment, you may need to consider that. But you also need to know what was the column effects. So this is our fixed, this is our linear models. he assumes that everything here is fixed, which probably also makes sense because the blocking factor in this case are factors that are well defined. If, for example, we can say water or shading, whatever it is. So the next model that we are going to build, we are going to use dilemma function. So this time we are going to have treatment as our fixed effect. We are going to have column as our random effect. We are going to have row as our random effect. And then we are going to use the same data, the Latin square. So this is the difference. When we are using a linear mixed model, we put our fixed effects, our random effects into a bracket, and then we have a 1, and then we separate with it. That can be explained later, but you can also go and read and ask why they do that. So we can run this as well. Let's run our model number 2. Okay, if you have not seen any red, the next thing that we can do now is let's get ANOVA for our model number 2, and we see whether there is a difference. Okay. So what you see now that when we ask for ANOVA from model 2, from the linear mixed model, the first thing that you see here on top here, they tell you that it's a type 3 analysis of variance with Satterthwaite's method. Okay. This is different from when we look at model 1. On top of model 1, they just tell you this is just analysis of variance, analysis of variance table. So there's a difference already we are observing here. Okay, so let's look at this one first again. Okay, so this one tells us the sums of squares is 155.8. The mean sums of squares 38.97. Numerator degrees of freedom is 4. Denominator degrees of freedom is 4. The F statistics is 12.7, and then the p-value is 0.00284. Let's look at this and compare with the results from the mixed model. Not the mixed model. Let's compare this with the result from model 0, which is the fixed model. So we look at this, everything here is the same. Okay, so you find the degrees of freedom is 4, and then the degrees of freedom for the numerator is 12. So that's the same as what we saw in the mixed model. So based on this, we are happy that at least the mixed model gives us the same thing like the linear models. And we indicated clearly that when you're dealing with a balanced data, you don't expect to get differences in results. When there is unbalancedness in the data, that is when you actually see differences in the result. But in addition to testing the fixed effect, now the mixed model also gives you variance components. Like remember, if you're interested in estimating the variance component, it can give you. So let's look at another way of looking at the results from a mixed model or from a model is let's ask for the summary. So we click on this. Okay, so the summary here on top, it starts by giving you that, okay, this is a linear mixed model fit by REML. T-test uses that. Method is, it gives you that. It gives you the formula that you use. It gives you the name of the data. It tells you this is a REML criteria at convergence is 9.63. I'll go back to my presentation and try to explain this again. It gives you the scale residue that the minimum residue is negative 1.33. The maximum residue is 1.35. And then it gives you an interesting table. This is random effects. Okay. So now it tells you that the column, the variation between the column from one column to the other is 0.24. Variation in the row is 3.756, and then residual variance is 3.066. So you can see in this case, we are not testing for column effect. We are not testing for row effect. We are estimating the variance that is associated with them. So that's what you see here. So, and this is the variance that will be important to you if you are interested in the variance component. Okay. Now, if you are to use the analysis of variance, then you need to do some calculations to get these values. And I'm going to show you how to do the calculation to get those values. So it gives you the variance and then the standard deviation, the variance and the standard deviation, the variance and the standard deviation. Okay. Then it also goes and gives for you the fixed effect. Remember, in the mixed model, in the fixed part of the mixed model, you are testing whether the different effects of the treatment effects are equal to 0 or not. So here we have the intercept, and the estimate for the intercept is 35.760. And remember, look here, there is B, there is C, there is D, and there is E. So that means A is not there. So A is part of the intercept. And the small p-value here indicates for us that this value here of 35.76 is statistically different from 0. Okay. Now, when we look at these other ones here, you find that B, C, D, the p-values are all big, greater than 0.05. So the effect of B is equal to 0. Effect of C is equal to 0. Effect of D is equal to 0. And then, but E is significantly different from 0. So in this case, we can actually literally say that treatment A, B, C, and D are not different from each other, but they are different from treatment number E. So to calculate the mean is going to be, you need to go back to our formula, the original formula that we had, Yij equals to the effect of the variety, the effect of the farms, and so on and so forth. And then it also gives you also the correlation for the fixed effect. So this is what we get from the summary of model 1. Let me answer some questions. This one I already talked about. No, I did. No, I said this one, I'll answer them later. I just wanted to finish them. It's the same one Ellen wrote on this side. Okay. Okay. So here we have the different effects. So what I'm trying to illustrate here is that the different models gives you different information. So in addition to testing the fixed effect, the random, the mixed model also gives you the different variance component. So from if you are interested in this variance component, then you decide how to use it. So like the question that I asked about whether you will go back. I asked whether if you are to go and do an experiment in the same place, whether you are going to use a Latin square or not. And we seem to see that the column, the variation from column to column seems to be very low. So we may not okay. 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 So we have this. So I'm going to start again. So here we fitted our our linear model, which is the first model here. And then when we summarize that first model, we got this output here. And this output here tells us that we are testing them. We are testing the row, we are testing the column, because we assume that they're fixed. But in the case of the linear mixed model, we only see we are testing. We're only testing the treatment which was considered as fixed. The rest were all considered as not significantly different. Sorry. The rest are all considered as random, and therefore they're only having the random effect, their variance estimate. We are also going to see later on. So somebody is saying, got the same error that I got. That is said, the file cannot open Latin square.csv, no such directory. That means you did not set your working directory to where the file is. Okay? You did not set your working directory to where the file is. So please allocate, please set your right working directory. Okay? So I'm going to look at the summary for the model one again and explain. I think somebody wanted to get an explanation again. So you can, as of now, you can assume you did not see those formulas. Just let's enjoy what is happening now on the computer. Okay. Okay. So this starts by giving us telling us what we have done, and then it gives you the criteria, and then it gives you the scale, the scale residual, and then it gives you the estimate for the variance components. So these are the different variance components. So the amount of variance in the row among the rows is almost the same as the residual variance, but there was little variation between the different columns. And then the effect here, let me try to re-explain. So here we're saying that the estimate for the intercept is 35.706. And this value here is significantly different from 0. The p-value is less than 0.05. So it's significantly different from 0. When you come to B, B is negative. So that means B is compared to the intercept is negative. So that means B here has a negative effect, but that negative effect is not significantly different from 0. The p-value here is greater than 0.05. When you go to C, is the same thing, 0.944. When you go to D, it's only E that is significantly different from the rest and different from 0. Okay. Okay, so the next thing that we are going to do is what about A? A is embedded in the intercept. A is embedded in the intercept. Okay, let me, so the next thing that I want to do is I want to see whether I can calculate the row and column. First, leave the correlation of fixed effects. I want to see whether the row and the when we change the row and the column and make them fixed effect, we saw that the variance that the REML estimated for us the variance between the different rows and the different column. So I want to see whether I can actually use the same I can use my first model, that is the linear models, and then and calculate based on the expectation. I want to calculate the variance that is associated with the rows and the variance that's associated with the column. So this is the formula that I'm going to use. We are going to use the row mean sums of squares minus the residual mean sums of squares divided by the total number of replications. So let me just call back my model 1. So model 1 assume that the row and the columns are fixed, and therefore it went ahead and tested where they're significantly different from where they're significantly different from each other or not. Now what I want to do, instead of testing them, I want to use this one here to calculate the variance for the row and the variance for the column, and I want to compare that variance with the variance that the linear model gave me. So what I'm going to do is I need to pick my row mean sums of square. The row mean sums of square is this one here. And then the residual mean sums of squares is this one here. And then the column mean sums of squares is this one here. So if I'm going to use my formula here, I need row mean sums of squares minus residual mean sums of squares. Then I divide by the number of replication. Some of you are making noise in class. I can see you're chatting now. Not you. But it's good you're helping each other. So I'm going to create an object called row ms. I'm going to assign it the value 21.85. I'm going to create another object called residual mean square. I assign it that value. And then I also calculate another one. I assign another, create another one called ms, column ms. And then I also try to, you say I use the same, you can use the equal sign, but you can also use the arrow like we know before. So once I have done this, I can then calculate the row variance. I can calculate the column variance. And then I put them together into a vector. So I can put the things together in a vector. I'm going to repeat. I want to name the values that I've calculated. The first one is going to be column variance. The second one is going to be row variance. And the third one is going to be error. So this step is just only to name. And then I want to print what I have here. So I print this. So you can see this is my column variance. This is my row variance. And that is my error variance. I calculated them based on my first model, which is a linear model. So you can get the same value as the value that is got in the linear mixed model, but you need to do some little bit of calculation. And that calculation, you can do it as long as you have a balanced design, and then the design that you're dealing with is among the design for which the expected values are available in the textbook. Otherwise, then you need to have your own interpretation. So I'm just comparing these two. So this is for the column, and you see for the column there is 0.2418, which is the same value. For the row, we have the same value, and then for the residual, we have the same value. So as much as you can calculate, you can use the linear model to estimate the variance component for a balanced design, you need to go through a little bit of the calculation and you'll be there. But if you fear calculations, then the best thing to do is to learn how to run a mixed model. Then you will automatically get the values that you're having there, okay? The next thing that we have is then that we have from here, we have here we have estimates of the different effects. So what we can do, we can actually calculate the confidence interval for the different estimates that we have here. So we can calculate the confidence interval for the variances, the confidence interval for the fixed effect. So I'm going to run this line here, and then I try to explain what goes on here. So just try to run this. You see now it is still doing some work. So if you see your console is telling you that stop, you can stop the thing from running. Okay, so this one has run and given me the results. So I'm going to explain these results a little bit. Okay. So the first thing that we have here is we have sigma. So we have sigma 1, sigma 2, and then we have sigma itself. So this one here is the standard. This one is going to be for the column. This one is going to be for the row. And this one is going to be for the residual. So remember the values up here. Let me give them back to you. I clean it up. So let me just get back a little bit. So these are the so we need so these are the variances, and then the standard deviation, these ones here. So these are the ones that we have their confidence interval here. So this one is from 0 to 1.5. This one is from 0.4 to 0.3 to 3.6, and this is from 1. Can somebody tell us how we can use confidence interval for hypothesis testing? I want to see, can somebody help? I want to see, well, how do we use the confidence interval for hypothesis testing? Okay, I can see inclusion of 0 implying not significant. They should fall within the set of boundary. So Clarice, good. We accept if the estimate falls significance at 9. Okay, so what we see here is that if 0 falls within your confidence interval, if you're testing hypothesis that this value is equal to 0, if 0 falls within your confidence interval, then you will fail to reject the null hypothesis. So in this case, we fail to reject the null hypothesis that the column variance is equal to 0. So we can agree that the column variance is actually equal to 0. And then for this one here, it falls between 0.4 and 3.6. So this one is significant because the 0 falls outside the confidence interval. And then for this is also significant. So you can see from here that the column variance is equal to 0, while the row variance and then the error variance are not equal to 0. Okay, so here we come and do the same. So for A, for the intercept, there is no 0 in the confidence interval. For treatment B, there is 0 in the confidence interval, so B is not significantly different from 0. C, there is 0 in the confidence interval, so C is not significantly different from 0. D, no significant difference, but E is significantly different because it falls 0 is not within the confidence interval. Kindly illustrate graphically. We are going to see that. The good news is we are coming close to an end. So let's gather the remaining energy to finish the last few minutes. I know you guys have been doing very, very well. Okay, so the other thing that I'm going to talk a little bit about is estimating the random effect. So the random effect is important, especially if you're interested in base linear unbiased estimators or BLUP or BLUP or but not BLUP. So what we can do, we can estimate why is treatment A included in intercept? Treatment A is used here as a reference against which the other treatments are compared. You can decide to fit a different kind of model, then it will be outside A. Okay. So what I want to do is we want to see the random effect, to estimate the random effect for the row, the random effect for the column. So we're going to use this function here. You run this, okay? So here what you can see is that row 1, the estimate is negative 2.67. Row 2, negative 0.55. Row 3, negative 0.0, and so on and so forth. So these are the random estimates for the effect of the row. And these estimates goes towards estimating BLUP, the best linear unbiased predictor. We can also estimate the random effect for column by using that. So you have here 0.2, 0.19. There are 5 columns, so each of them has an estimate. Now we can compare that to if we assume that they were fixed. If we assume that they were fixed, then we would see different estimates. So let's assume that they're fixed. Okay, this is where I got my red. So this one is telling me, I know all of you might get red, that use method model.table, no application for model.table applied on the object from LM. So what I'm going to do, I'm going to run my model 0 with AOV, with ANOVA, then I come and try and see whether it will work. That is what we call hacking the system. Okay, so you see now that's why I had to, so I'm going to run this one here. Okay, I think I have something missing on my, at the end. Oh, I'm supposed to put, good. I don't fear red. Once I see red, I'm happy because I'm going to get something new, or I'm going to discover my weakness. Okay, so now it has run. So the next thing that we're going to do now is we're going to say good news for the certificate. The certificate will come. Don't worry, just concentrate and we'll get the certificate. Okay, I'm trying to run this again and see. Yeah, it's run. Okay, so I'm going to look at my fixed effect and I'm going to compare it with the random effect. So these are my fixed effect for treatment. These are my fixed effect for row. And these are my fixed effects for column. So these are estimated as fixed. And then let me bring back the other one so that we can make a comparison. Let me bring the column one down here so we can. So you see for column one, the estimate for the fixed effect is 0.8, but for the random is smaller. And then for 2, 0.75, for the random is smaller. So in all cases, the random is smaller. So the random effect is smaller, and that explains what we call about the random effect having a shrinkage effect. It shrinks. Okay, so you can compare that with so we compare with the column. What we are going to do now is we are going to look at the ratio of the fixed effects to random effect to see what is to see actually how they perform. So what I'm going to do here, I want to calculate the ratio of this is my random effect, because model one, remember model one is our random effect mixed model, and then this is from our fixed model. So what we're going to do is we're going to run this. So if you compare the ratio of the random effect to the fixed effect, the random effect is about 0.8%. Okay, it's lower than the fixed effect, and it is constant. That ratio there is constant. Now, if you compare for the column, you see the value is 0.25. So what this one tells us that the random effect is always smaller than the fixed effect. For any effect that you're trying to estimate, if you assume that the effect is random, you're going to shrink the estimate. You're going to shrink the effect if compared to if you consider to be fixed. Somebody asked for the graphic, so I'm going to draw the graph for this, and then we compare. So let me share. Okay, so this is for the effect from the different columns. So you can see from here that 0 is here, and then these are the confidence interval for. So this is the effect of column number 1. So effect of column number 1 range from negative 0.5 to positive 1. So 0 is in the confidence interval. The effect for 2, the effect for number 3, the effect for column number 4, the effect for column number 5. So the column effect are actually not significantly different from 0, as you can see from this. Just hold on a little bit. Let me get my system sorted. Oh, say, how did you remove the, how did I remove the error? Okay, let me just try to rerun the thing again. Okay. So when I was fitting my model, the error was related to this model here, model 0. I fitted model 0 in two ways. I fitted using LM, and then I also fitted the same model using AOV. Now, by using AOV or using M, you get different kind of objects. Oh, sorry. I think I'm not sharing my script. Sorry. Okay, you can see my you can now see my script now. Okay, so the error was made in relation to this model. So the first time we ran the model, we created the model using an LM function. And when you try to use an LM function into our I think it was here. When we try to use it here, so let me just change the model, then I run it, and then I show you the error. Then I can go back and and change the story. So the first running, we ran it with this. And then we went down to try to estimate the effect. Using this. And then it gave the error. So the error here is telling us that error in use method, model.table, application method. So it's saying application method for model.table applied to an object of class LM. So it's saying no application method for applied to class LM. So we don't, it doesn't accept LM, something created by LM. So we need to go back and try to create another model, but this time using the AM, not the LM anymore. Okay. So that's why I went back here and then ran my second model now, but I use AOV. It's still the same model, but I've just changed the way I changed the function that I use for calling it. So I changed that. Now we can go back and run the same script that I refused to run. And this time we should be able to get our results. So it's the same one here. So after running this, now we don't have any problem now. So that is sorted out. Is that clear to the person who asked the question? So it's the same model that we create, the same model, but we use different function to create it. Yeah. And so the thing is a bit, it takes in, because the way because you see somebody could have developed is the program to use only a particular object, and therefore if you change the object, then you actually don't run it. Yeah, so next time maybe you can complain to the person, then the person will modify. The next update may be able to take the LM object as well. So the next thing that I wanted to do is to run a dots plot for the row. We saw for the column, and according to the one for the column, there was no significant difference because 0 is in the confidence interval. So let's run a dot plot for the confidence interval for the column effect as the row, rather not the column. Okay. So from here, you can see that these 2, 4, and 5, their confidence interval is outside 0. 0 is outside the confidence interval. 1 also has 0 outside the confidence interval, but 3 and 2 and 3 have their confidence interval within the 0 is within the confidence interval. So these 2 are not significantly different from 0, while these 2 and these ones are significantly different from 0. That is what you have. So that's what we managed to show here. So the next thing that I want to show, I think I'm almost coming to an end. So now we talked about the BLUP, which is now the prediction. So assuming now you want to make a prediction about a new or unknown individual. So let's say, for example, we want to have a prediction about a new offspring of a bull. So we can use this formula here. So when you're going to combine the fixed part of the model with the random part of the model to give you the prediction. That's why we call it a BLUP. We have the fixed part, we have the random part. Now, remember we talk about the random part as shrinking is smaller than the fixed part. So it's also going to affect how the mean value of BLUP, the BLUP is always smaller than blue because of the shrinkage that happened. For those ones who would do breeding, the shrinkage is related to irritability of the trait that you're handling. So if you're an historian like me, then you don't need to know that. So these are the predicted value for the different columns. And then different rows rather. And then these ones are the predicted values for the different columns. So column 1 is still used as the baseline, and then the other ones have their value added onto that. So these are the BLUP or the predicted values that you have. Okay. Now I'm going to do something that is going to be more interesting to you now. Somebody said I have a lot of energy. Oh, you guys give me all the energy that I'm using today because you've sacrificed a lot. So I also need to put in. Now, what I want us to do now is I just want us to do something very, very simple. Any other question there that you think I need to answer? Okay. Please don't shut off your head now. I know it's coming to close. Okay. So what we want to do now is we want to compare the different models. Let's say, for example, I create a model that only has treatment. It doesn't have the row and it doesn't have the column. And this model here I'm creating using the linear model because this is the fixed effect. The treatment is a fixed effect. I want to compare it to model number 3, which I'm going to have the treatment, which is a fixed effect, plus row as a random effect, but it doesn't have column. I also want to compare the same model with another model that has treatment and then has column, but not row. Now these are nested because model 2 is part of model 1. No, it's part of model 3. Look here, this part of model 2, because model 2 just has yield with treatment. So you can see it's actually here is also there. So it doesn't have this. That's why I say it's nested within. So one model is nested within the other. So I can compare this model here. I can compare 1 and 4. No, not 1, 2 and 4. I can compare 2 and 3. And please forget about the script now. Let's look at the outcome, the results that come out of it. So I want to compare model 2 and model 3. The question that I'm asking myself here is there a difference between a model without row compared to a model with row? I run this. Okay. So now what happens here is then I have a statistics here. So the comparing two nested model, what happens when you're comparing two nested model is that you're going to look at the difference between the two model, and then that difference, we are going to assume that it has a chi-square distribution. So what we see in this case is that we look at the p-value here, and our p-value here is 2.5 times 10 to the power negative 5. So that is 0.000. So based on this, we can actually see that adding row to a model with only treatment improves the model significantly. So the two models are actually significantly different. If we compare model with the treatment only and with one with column and treatment, we're going to see that the two actually are not any different. So you can see here, well, it's still significant. So adding row, adding column to the treatment significantly improves the model. So in this case, adding both row and column are good for your model, makes your model better. So it's important to add the random effect of the row and the column in the model if you're adding one at a time. The reason why we have to create a little bit of a function here is because we cannot run a fixed effect only model in LMER. But if you have a model that are both created by LMER, then you don't need to write this long thing here. What you simply need to do, you simply need to write ANOVA and put the two model that you want to compare together in bracket, and then you run, then it will tell you whether these two models are significantly different or not. So here we are comparing a model with row and treatment to get versus a model with row, treatment, and column. So this is our full model versus our sub model. So here I can have, so I'm comparing a model 3, which has treatment plus row, with a full model which has treatment plus column plus row. And when I do that comparison, I actually see that I get a chi-square value of 0.25, and then with 1 degrees of freedom, and then the p-value here is 0.65. So what this one is telling us is that you don't actually need a model with both row and column. You only need a model with the row, and that should be that should actually fit for you, your data very well. Now, if we compare our model with the column only versus the full model, okay, we have a red here, which is a good one. Okay, so it's telling us warning here. In HopRap, Optimizer, Deviant, Convergence, Trusted Region. So it's telling us that something is not right with our model. So don't rush to interpret this model. First, you need to try to see what is going on within. The reason why this happens is sometimes it has to do with what we call convergence. Because the way this mixed model works is that it starts by selecting some values, putting it in the model, calculates new values, put the new value in the model, calculate other new values until it reaches a point when there is no more change. And that is when it will stop, it will converge. So in some cases, for some data set, there may be some problem with the conversion, but that is going to be a topic for another day. So here, if you look at a model, with the comparing a full model, that is the model with both row and column and treatment, with a model with only treatment, you see a substantial difference. So including only row, only column in the model is not good enough. You need both of them. But if you compare the long model with a short model with only row, you realize the row is okay. So that's why I said in this, what you learn probably from this experiment, from this analysis, is that sometimes when you design your experiment, you go to the field. When you come to do that analysis, you realize that what you thought was a good blocking factor may not work. So it can help you next time to design your field experimentation better by borrowing the information that you use, that you've got from your previous study. So I'm not sure whether I should run a little bit more, but because I think probably people are exhausted. Is the director on board now? Check first. He's on. So what do you people think? I ran the repeated measure and stop there. Okay, so my colleagues accepted that I disturb you a little bit more, but it's going to be, with your permission, of course, it's going to be only for a few minutes. Then we'll actually call it a day. We ask the director to give a few words, and after that, we can. He will tell us about the certificate that we are working on, but you receive. Okay, then maybe somebody from Reforum will say a word or two. Okay, then Madam Susan will represent the facilitators and say also a word or two. Okay, so now this one here, you just, I mean, if you get error, what, don't run this. I'm going to run this alone. Then we are going to see. So this is a very interesting study. The study is related to vision. You want to, you're trying to use the power of vision. So it is you get a number of people. There were 7 people, and each person was made to they increase the power of some power that they increase, and then you are supposed to make observation. So they are measuring what we call acuity. If you go and you go look for this particular package, you'll get it there. So I'm going to bring that data in. Just watch what I'm doing now. I'm going to explain a few things here and there. So I'm going to draw a plot and use that plot to explain a few things here and there. Okay. So what happens here is that you're trying to increase the power of, say, lens, and then try to I mean, here you have two eyes. You have the left eye and then you have the right eye. Of course, the issue of dependency comes in that if the two eyes are belonging to the same person, then they are more related. So observation made by Susan with the left eye and with the right eye are more related than the one made by Susan with the right eye made by Ellen with the left eye. So that is the kind of things that come in. So you need to take that into consideration when you're doing the modeling. So from here we can see that actually at the for individual number 1, the difference between the left and the right eye seems to be okay, but the number 6 seems to be having a problem, because you can see there's a big difference between the left eye and then the right eye for the beginning, like from 6 out of 6 and 8 out of 6 is when it, at 6 out of 36 it converges, then again the thing diverts. So what we have here is that there is dependency because observation comes from the same person over this particular number of the different power. So there's dependency on the person, then there's also dependency on the eye, because you have the left eye and then you have the right eye. So if it is the left eye and from the same person, 2 observations from the left eye of the same person are more related than the one from the left eye and the right eye of the same person. So that's the kind of dependency that we are dealing with. So this is a data set, a very interesting data set that we are going to explore just briefly, and then we call our day off. So I'm going to run a simple linear model, not linear, mixed model. So we are using the same function. So this time we have the acuity, and then the fixed effect is the power. That is because they're selected purposely for that study. And then we are allowing variation between the subjects, but we are also allowing variation between, I mean, the eyes in the same subject. So there is also a different layer here. Either you can be the same, the left. So there is correlation relating to the left eye, correlation relating to the right eye, and then correlation relating to being on the same person. So we have 2 layers of introducing dependency, one at the subject level and one at the high level, the high within the subject. This is similar to actually our Betty and the farm. So the data is the vision. We can run this model. Okay. So this is my model number 5. So I'm just going to have a summary of model number 5. Okay. So it tells us our model. This is our fixed effect. This is our first random effect. And then this is our second random effect. So we are introducing correlation at the individual level and correlation at the eye level. So same eye, same person, more correlation. Same eye, different person, some or no correlation. Okay, so here we have the random effect like we've seen before. So this is the variation. So you can see actually there's also variation as you move from eye to eye. So there's variation between the left eye and the right eye. And then there's a variation as you move from Susan to Ellen to myself. That is also the variation. And then there's that other variation that is the noise. So these are the different values that we have there. Then of course the fixed effects, now we are comparing the different power, 6 out of 18, 6 out of 36, 6 out of 60, and you have the t value, and then you have your t. So what you can see here is that it is only variation at 6 out of this, and then the intercept that differs. So I think you can study this from here. And then we have that correlation. So I'm going to do now one last thing. So what I want to do now is I just want to show you that what it means to generate the correlation. So I want us to look at these figures here. So the issue here is then that if I'm looking at, I have correlation at different levels. So these are my three. I have variation at the eye level. I have variation at the subject level, and then I have the variation at the noise level. So the variation at the subject level is going to be related to can you see now? Okay. So let me wind up and let me just wind up here now. So I'm going to calculate these two values, and then I'm going to compare them. So the one that we have calculated here, this is the correlation of observation coming from the same person. Okay, so different eyes, the same person, this is the correlation. And then the same person, same eye, this is the correlation. So that means if the observation, all observation coming from your left eye are going to be highly correlated compared to one coming from the left and then coming from the right. So I think it would only be prudent to stop at this point. I'll ask you, this one's here, all this remaining one, we ran them already when I was talking about the incomplete block design, and we're talking about split plot design. So at this point, I would like to thank all of, because on my own behalf, Susan is going to talk on behalf of all of us. I would like to, okay, as he said, I talk now on behalf of everybody, so that should be fine. So I would like to really express our sincere appreciation to all the participants for being with us for the last 2 weeks. I know it has been a very, very, very hectic schedules. We understand, but we also know that the interest is there because there's need to use the available, to use these tools into your studies. So we are really grateful for all the effort that you people have shown, put in, and we hope that we will have another course very, very soon. So at this point, I would like to call somebody from Reforum. Is Jolene on? Is David in? Adija? Adija, can you say something on behalf of Reforum?
Thank you very much, Professor
Okay.
Thomas. I thank you all our facilitators for all the knowledge that they've given to us with all their hearts. And I'm very sure that our participants are going to really use this knowledge for their benefits, for their studies, and for their careers. I thank all the participants for making time to participate, despite the challenges of bundles, internet, and anything. And I wish all of us all the best in the future. I will not say much because where I am, it's not such a very comfortable place for the long speech. Thank you so much.
Thank you very much for the beautiful speech. Can I now request the Director of Mercy, Dr. Richard Edema, to say a few words to the participants? Richard, you're welcome.
Good afternoon. Thank you, Thomas. I hope you all hear me very well.
Yes.
I will put a small video. I think you can all see me. But I'm really grateful that we've successfully come to a close of this meeting. To see so many people spending their weekend and sacrificing, I know, to be on a course like this really shows the importance you've taken on the opportunity that has been given of learning. Saturdays are normally for weekends, for relaxing, and for some people to go to beaches and have a good time. But you are here learning. I'm grateful. I also would like to extend my appreciation to the facilitators. Thomas, Susan, Helen, you've been great. I think you've won yourself a lot of followers who are enthusiastically following you, even on YouTube. I've been on both sides. I think you've really designed an excellent course. It seems it's meeting the need. And people can't take enough. I've read a few reactions on the chat with even people wanting more. So I think this is a great opportunity. Knowing this, I think we will keep thinking of different ways of how to keep supporting such a popular course. I know statistics is really at the heart of everything. You can't do your research, you can't do anything without a good interpretation of that data, and that needs statistics. So I know this was a large course. There have been specific requests for different aspects of this course and others. I think that will be issues that we'll discuss and with facilitators. And as Mercy, this is really what Mercy has been created for, to really contribute into the human resource development of Africa. And we're glad we are really offering it as PhDs, as MSc. I've just posted the website. I didn't want to talk too much, after so many days of listening to talk and doing things like that. You don't want to keep you don't want to give a very long speech. Yeah. But thank you for really attending this. Thomas has been repeating it over and over in time, and the facilitators. It's very important that you really respond to the surveys and telephone calls that our funders will give it to you. We've taken your data, we've taken your emails, and actually personal phone call for mobile phones This is really not an intrusion to your privacy, but it is just to show the funders that you are real. You are not computers answering on it. You know these things. Thomas, what is this thing where you have to feel to just show that you are not a computer? You know, for some of these.
Yeah, what do they bring for you all these things? Yeah, you click where there's a light or.
Yeah, so they want it for real. And if you really help us in responding, it is going to trigger more funding for us to enable us to do such more short courses with you, and not just short courses. It's also allow us to provide scholarships for MScs and PhDs at our center. Our center is an African Center of Excellency, and it's just like in West Africa, what WAC is to West Africa, and SCCI is to the Southern Africa. And I think as Africa, it is important that such centers contribute the way they are. We need to build our own capacity. The statistics that you've done now, I know you look at it in a small, literal way, but you're going to go down there. You are really human resource that is going to address pertinent issues in Africa and contributing to our visions of 2063, 2050, the African AU vision to build the Africa we want. And without well-trained and skillful people to push the agriculture agenda, to push the water agenda, wherever it is, in fisheries, in crops, wherever it is, we're not going to go anywhere. And we need to build our own capacity. So you are look at what you're doing as a small bit of the bigger picture. The statistics is killing you to address things down that chain. You are a key pillar, a brick that we're putting together to make Africa work. You know, we cannot always be thinking of skills where we do not address us resource base. We are a young continent full of youth, and many times many of these people don't even have jobs because we can't prepare them enough, and they go on boats across, and sometimes they get the misfortunate of drowning and or go to Southeast Asia. This migration of labor cannot go on. So when we're training our own and getting centers like this to do it, it is very good. So in this regard, I really want to pay tribute to Reforum for championing a lot of this continent-wide capacity building institutions. 10 years ago, Reforum started a small breeding program at Makerere University that has now become a center of excellence. So we actually created out of a regional program of Reforum. So we're grateful to the executive secretary and all the staff of Reforum who have actively been involved and supporting this course for the last 2 weeks. So I really would not like to continue on, but the issue of certificates, that one we will do. I think we will work with the facilitators. We have all your data, your names are all there. So we'll see how best we can issue that. Thomas, I think that would be like a digital version of it, right? We can post it all over. Yeah. I think we will do that. We promise it will be there. We'll work on it. Just make sure that all your you've registered on our database, and we'll use that to do it. So it's been heartwarming to see more than, I don't know what the last number is, but it was over 2,000 people who participated in this course, either throughout, others at different times. Just lastly, we recently, as Mercy became a host center for the partnership for skills and applied science and technology PASET, part of a World Bank project. Basically, we will be hosting through a scholarship that will be run in Nairobi, students who are interested in doing PhDs in plant breeding and biotechnology based at Makerere. It will be advertised every year, and you get that opportunity. Nobody is bad. It is a continent-wide opportunity for those who are interested in doing it. You can Google it up. The Regional Research Fund, RECIF, and PASET, and all of the Massey Secretariat, all get in touch with me on whenever these opportunities come. So I think I would like to stop here and again wish you all the best in all your endeavors that you are doing wherever you are, in your home institutions. Aluta continua, let's continue pushing the African agenda. It's only Africa can only create the Africa that they really want, which is food sufficient, which is a good place to live in, free of wars, free of everything. So thank you very much. I stop here.
Thank you very much, Richard. I see people have been saying hello, Ellen, so I think Ellen can say a word before I close. And Susan, okay, so Ellen, what? You can greet your people.
Okay, thank you so much, all participants. It has been great time being with you for the 2 weeks. And I'm so happy and excited from how the progress has been, that you've learned a lot. I encourage you to go ahead and practice with R according to the data that you have. You know, with data analysis, it's about practice, practice, practice. Don't just keep these things, go ahead and use them on your personal data. I guess as you journey on in your career, you really like the part of data analysis that is really very interesting. Thank you so much. It has been great, and I wish you all the best. Susan. Hello, participants.
I'm so grateful for having been part of this. And I would like to wish you success in your endeavors. Thank you for being excellent participants. You've really given us energy to go on and train the whole 11 days. We could even do it for a month, but the energy comes from you. Because you've been excellent, you've really pushed us to give you more. There is more to come. It will depend on organization, it will depend on what God has for us in stock. We thank you so much. We wish you God's blessings in everything that you're going to do. I would like to take this opportunity to thank the funders, Mercy, Reforum. We are so grateful for choosing Helen, Thomas, and me to facilitate to the whole of Africa and maybe the world. We are so grateful. Thank you so much for sparing your Saturday. For those who are supposed to go to praise God today and they are here, we are really very sorry, but we hope God will forgive us for keeping you busy today. Thanks so much, and I've posted my email. I have posted my email, and please keep in touch. We'll keep in touch with you, but if we don't answer immediately, don't get angry with us. Have a nice time. Thanks for being great participants. Kwaheri. I think that's all I know in Swahili. Thank you so much. Kwaheri, Kwaheri, Ethiopia, Kenya, Uganda, Nigeria, Cameroon, Gabon, Sudan, Nigeria mentioned. Bye-bye. You're so great participants. Rwanda, Hong Kong, Kwaheri sana, India, Somalia, Tanzania, there's even Wakanda, Zimbabwe, UK, Burundi, Kwaheri, kwaheri. You are great. Zambia, thank you so much. Thank you. Please, when they invite you for another one, come. There's no end to learning. You can see me, I have white flowers in my hair, but I'm still learning. So there's no end to learning. Thank you so much. Yeah.
So thank you very much, colleagues. Just to re-emphasize a few things. The links are going to be active for the next 2 weeks. Please make sure that you get the material. You can share with your colleagues. That is fine. Hey, sorry. Hey, sorry, I think. So thank you very much, colleagues, for this. I'd like to emphasize one thing again, that the links are going to be active for the next 2 weeks. So please ensure that you get the material. Secondly, I posted the website for SCIPSA. I posted it on this, but you can always try to look around. You're asking for emails, you're asking for telephone numbers. If you really want to see Ellen, please, you look for her email in your own way and you get her. So please, when they come, when you're asked about the course, please, we need feedback, and the feedback will help us to organize other courses. So thank you very much. I think we can call it a day. Bye-bye.
Bye, everybody. Bye.
Yeah. Don't forget to come to study in Makerere. We'll teach you, all the three of us will teach you physically.
And you'll see the picture as well, the photos. Bye-bye. Thank you. You're excellent. Don't forget to practice, practice, practice. If you keep, you'll forget everything. Bye-bye.
Please get the Telegraph group and make sure you keep in touch with one another. Good.
Okay, bye. I'm gonna leave.